This is going to be the lecture over section 28.7. We're going to be looking at wave-particle duality. So neither the momentum nor the position of a particle can be measured simultaneously with arbitrarily great precision, which is something different that we've experienced up to this point. In classical physics, you can do that without too much difficulty. Instead, the uncertainties in the two quantities play complementary roles. The less the uncertainty about a particle's position, the more uncertain is the momentum, and vice versa. So this is described by Heisenberg's uncertainty principle. In other words, the uncertainty that you have in the position times the uncertainty that you have in the momentum is going to have to be greater than or equal to Planck's constant divided by 2 pi. It has to be. This is not negotiable. This is something that is, and you will accept it whether you like it or not. So let's go and let's take a look, see what the section has to say. So in classical Newtonian mechanics, we think of a particle as a point. At any instant in time, it has a definite position and definite velocity, but in general, such a specific description is not possible. When we look at a small enough scale, there are fundamental limitations on the precision with which we can describe the position and velocity of a particle. Many aspects of a particle's behavior can be stated only in terms of probability. So let's take a look at the single slit diffraction. So we're going to review an optical single slit diffraction experiment. And you got a light beam that is incident on a narrow horizontal slit, and if light travels only in straight lines, the pattern on the screen would be shown in figure 21a. The actual pattern is a diffraction pattern showing the wave nature of light. In other words, you would think you would see this, but what you actually see is this. Detailed analysis shows that the width of the central maximum in the pattern is inversely proportional to the height of the aperture. Most, about 85% of the energy is concentrated in the central maximum. In other words, right there. Now we perform the same experiment again, but use a beam of electrons instead of monochromatic light. We have to do the experiment in a vacuum so the electrons don't bump into the air molecules. When we can produce the electron beam with a similar setup in principle to the electron gun in the cathode ray tube. Produces a narrow beam of electrons that all have the same direction and speed, and therefore also the same de Broglie wavelength. So you've got all these electrons in a vacuum coming towards a slit. The components of momentum of an electron striking the outer edge of the central maximum at angle θ1 is shown here. You got your photographic film. So the graph shows the degree of exposure of the film. In other words, you're seeing the exposure of the film here. Most of the stuff hits here, but you still have things that are hitting out here. So the result shows a diffraction pattern identical to the one that you saw earlier. Most, or 85% of the electrons strike the film in the center region, but a few strike farther from the center in the subsidiary maxima on both sides. The electrons don't all follow the same path, even though they all have the same initial state of motion. In fact, we can't predict the trajectory of an individual electron from knowledge of this state. The best we can do is say that most of the electrons go to the central region, few go to other regions, and so on. So we can only describe the probability that an individual electron will strike each of the various areas on the film. This fundamental indeterminacy has no counterpart in Newtonian mechanics, in which the motion of the particle can always be predicted if we know the initial position of motion with great enough precision. So we've got fundamental uncertainties in both position and momentum, and these two uncertainties are related inseparably and in a reciprocal way. Basically, it means the more you know about one, the less you're going to know about the other. The uncertainty in the y position is determined by the slit width A, and the uncertainty in the y component of momentum is directly related to the width of the central maximum in the diffraction pattern. If we reduce the uncertainty in y by decreasing the slit width, the diffraction pattern becomes broader. In other words, you end up with a relationship like this. So in general discussions, The uncertainty of a quantity is usually described in terms of statistical concept of standard deviation. In other words, it's a measure of the spread or dispersion of several numbers around an average value. So if you have an x coordinate that has an uncertainty, and if the corresponding momentum component has a specific uncertainty, then the two uncertainties are found to be related in general by an inequality named for Heisenberg. Not Walter White. I'm talking about Werner Heisenberg. So you've got the Planck's constant, and you've got the product over here. Same thing holds true for energy and the time interval in which the system remains in that state. So you've got a few problems there that you can work through.